where u and v are functions of x and y and z equal to xy. So let f of z be a function of a complex variable. F of z is said to be continuous at z naught. If limit tends to z naught, f of z equal to f of z naught. That same definition as real numbers. Now, if derivative also, the definition is same. In case of real functions, we know f dash x is h tends to 0, f of x plus h minus fx divided by h, provided the limit exists. Here, same thing. Just in place of h, we have del z. Because it means this is a complex variable. Complex number approaching 0. So we have h tends to 0. H tends to 0 means h is a real number which is approaching 0. In case of real number, if we want a graphical representation, we have a straight line, isn't it? That real line. So we can move only in one direction, or you can say two directions from left and right of a given number. Now, in case of complex numbers, there are infinitely many directions because now we are dealing with a plane instead of, because it is two-dimensional. In complex variables, there are two variables involved. Z equal to x plus iy. It's x and y. One is real part, other is imaginary part. Two in the first two dimension. For present the Euclidean, in fact, we call it an Argand plane because it denotes the imaginary unit. So in is there. So we can move to that point from in directions. Where tends to 0 means there are directions by which we can approach 0. But in numbers there were only two directions. Written only h tends to 0 plus h tends to 0 minus. Right side of 0 or side of 0. But things are not in this numbers because 0 plus will not have a meaning here because there are so many other directions also. Okay, so there is one balance between this real functions and complex functions. A number or a real number, we can approach a particular number in two directions, from its left and right. But for complex number, we can approach the number from an infinite number of directions. Now, there is another analytic function. If the derivative f dash z exists at all points z of a region. Region means an open and connected set, and z is said to be analytic in R. I will share soft copy of a book also, from where you will find the details and some geometry explanations so that you can understand properly what these things mean. So derivative, a function differentiable at a point and analytic at a point is slightly different. A function, a complex function, and that derivative exists point is differentiable and its domain. So we'll understand later more clearly it means analytic. Analytic means differentiable. Analytic at a point means it is differentiable at all points in its neighborhood. So here more mathematically, more precisely, we have given the definition of analytic. One important equation for determining differentiability of complex functions is Cauchy-Riemann equation. This result is that a necessary condition that f of z be analyzed in a region R is that UV satisfy the Cauchy-Riemann equations. The Cauchy-Riemann equation del u del x equal to del v del y, and del u del y means partial derivative of u with respect to y equal to minus of partial derivative of v with respect to x. In short, we can write that is ux means partial derivative of x, derivative of u with respect to x is equal to partial derivative of v with respect to y, and partial derivative of u with respect to y equal to partial derivative of v with x. What are u and v? U and v are this. F is a function. We can always separate its real part and imaginary part. So that is u and that is v. One example is, suppose f of z equals square. Z square means what? Z means x plus iy whole square. So we can separate the real and imaginary part. So real part becomes this x square minus y square. This is u. This u. X square minus y square, and this is v. I into 2xy. So this is v. So if these two conditions are satisfied by this equation, then it will be called analytic at that region. Means at every point it is differentiable. Right now you may not be understanding properly. Read again carefully. There is a function before. Later on we will come to that harmonic part. Which one should we discuss with that is differentiable then? Okay, let us see this example. Show that derivative of z equal to z bar does not exist anywhere. Does not exist anywhere. That what is fz is nowhere analytic. So analyticity and differentiability are somewhat synonymous but not exactly same. When you do the examples, you will understand their actual difference. This function, let us consider that f of z equal to z bar. Z bar is what? Z bar. Anyone?
Changing the sign of the imaginary part. If x plus iy is given, then x minus iy.
X minus iy. So this is called conjugate. So if x is x plus iy, then z bar means x minus iy, which is called complex conjugate. The function here, input is a complex number and output is its conjugate. We have to show that this function is not differentiable anywhere. So let us see by the f dash z equal to same definition, limit del z tends to 0, f of z plus del z minus f of z divided by del z. So now here f of z bar, so f of z plus del z will be z plus del z bar, and here also f of z will be replaced by z bar. Z bar del. And now del tends to 0. Del z is what? Del z is del x plus I del y. So if del z tends to 0, then we have del x tends to 0 as well as del y tends to 0. So here we expand these things. We replace z by x plus iy. We replace del z by this. Then we replace z by x plus iy. Then we have this expression, and again del z equal to del x plus I del y. Now if we simplify, and remove the bar, like x plus iy, its term will be the conjugate line of this imaginary part x minus iy. Here also, it will, this bar means this bar plus this bar. So bar of this x plus iy is x iy. Bar of this del x plus I del y will be del x minus I del y. Okay. So after simplification, we have this. Now let us take the limit. So further we can simplify and some terms get cancelled. Like this iy. And the rest what remains is del x minus I del y divided by del x plus I del y. Finally, only this expression remains. Now you have to take the limit. In the question itself, it is given that you have to prove that the derivative does not exist anywhere. So when the derivative does not exist, in terms of limit, what you can say? Or from real functions. When do you say that limit does not exist? Means when the limit is not unique. For the existence of limit, the limit has to be unique, and it should not depend on the path to which you approach that point. Here we are talking about del z tends to 0. So by whichever path you approach towards 0, this limit should be unique if it has to exist. Otherwise, the limit will not exist. Means if you can show that when we move towards 0 from two different paths, we are getting different values of this limit, then the limit will not exist. The limit has to exist, it has to be unique, and it has to be independent of the path. So now, as I said earlier, in case of complex plane, there are infinitely many directions to which we can approach a particular point. Here 0 is the point, so we can approach, so you can visualize. There are so many paths. So if you can show that you are approaching 0 by two paths for which you are getting two different values of the limit, then the limit definitely does not exist. So that's the approach we'll adopt here. So first let us see approach 0 along real axis. So now if del z tends to 0 along real axis, of course we can do this. We can approach 0 along real axis. So when we move along real axis, the value of the imaginary part. For example, 30 is a point in real axis. What is the value of its imaginary part? 0 only. 3 is the real part, imaginary part 0. So similarly, if you take any point on the real line, its imaginary component is always 0. So there is the thing, when del z tends to 0 along real axis, then the imaginary part is always 0. Okay, so in this limit, what will happen? Only del x tends to 0 will remain. This del y part will become 0. This is 0, this is 0. So get rid of this. These are 0. So now if you take limit, it becomes limit del x tends to 0 del x by del x. Del x tends to 0 means del x is not 0 itself, it's approaching 0, it's non-zero. So del x gets cancelled. It you get as 1. Understood? Ask me if you have any doubts. What we are telling is that del z tends to 0 along real axis, means The imaginary part is always 0. So this becomes 0. This becomes 0. What hence is del x by this. Del x by del x means you can cancel them and you will have 1. Okay. So this is one limit when you approach 0 along real axis. Now again, if you approach 0 along imaginary axis, then what will be the real component? Ankush.
Yes, sir.
Yeah, when we approach 0 towards imaginary axis, along imaginary axis, then which component will be 0?
Sir, real component
Real
del x. Real component del x
will be
equal
0.
to. Yes, sir.
Right. Right. So del x 0 means this is 0, this is 0. So what remains? Minus of ideal y divided by plus ideal y. Now I gets cancelled because I is non-zero. Del y also gets cancelled. They are non-zero. So what remains? It is minus 1. Okay. So these are the two limits. When you approach 0 along real axis, you get 1. When you approach 0 along imaginary axis, you get the minus 1. So that means the value of this limit is dependent on the path through which you are approaching 0. It's not unique. When it is not unique, definitely the limit does not exist. This limit, we say that it exists is whichever path you take. Okay, so therefore, since this limit does not exist, hence we have proved that the derivative of z does not exist anywhere. We have taken an arbitrary point and we have shown that this limit is different when you approach 0 towards different paths. We have just taken two different paths. So since there are infinitely many paths, the easiest paths to take are the real axis and imaginary axis. You can show by any other path also, but why to go for any other path? Because these two are the easiest ones. In some cases, we will see that they don't work because if you approach along real axis, then if you are getting 1, and next you approach along imaginary axis, then also you are getting 1. Then you have to go for other paths. Okay. But here this works. So first we will try by these two paths when you have to show that some limit does not exist. These are the easiest paths to take. Okay. If there's any doubt, you can ask me. Right now I can also understand everything is not clear to you. So you study at home. Next class also you ask me if you have any doubts. This complex analysis is just an extension of that real analysis part. We are just replicating the things, but it is not simple replication or extension because many things are different here. One major difference we have discussed that in case of real number we have h tends to 0 and h can tend to 0 only from two sides. But in case of complex number, when we write del z tends to 0, there are infinitely many ways by which we can do this. We have shown it by two ways only. Okay, so we have shown here the derivative of this function f of equal to z bar does not exist anywhere. So it is not analytic. Next, another result is proof that if fz is differentiable at a point z0, then it is continuous there. Writing is not clear. It is continuous there. This result is same as real variable functions. In real variable also we have this same result that if a function is differentiable at a point, it is continuous there. In case of complex variable also it is true. Here is the proof. read it. Proof is there. I will share a book also where you will find the proof. You read it first. There is no point me explaining this right now. If you're understanding, fine, but you may not understand. So if you follow the techniques, you will understand. Next, but if you don't understand, you ask me. That's same thing. We just have to show that it is continuous at a point Z naught. And by continuous at a Z naught, what is the necessary and sufficient condition? It is that if limit Z tends to Z naught f of Z is equal to f of Z naught, if this part you can show, then it is continuous at Z naught. We have just done some algebraic manipulations and have shown that part. You read the proof, try to understand. You have it. Now let us see this problem. Is this function f of Z equal to Z square plus 1 if Z equal to I and equal to Z if Z equal to I differentiable at Z equal to I? So try to solve it. Tell me if this function is differentiable at Z equal to I. How will you do this? So there are several ways. First of all, you can go by that formula, like previous problem, finding its derivative by definition, that you can do. Or some other easier things are also there, that this result tells you what? This result tells you that if a function is differentiable at a point, then it must be continuous at that point. Okay, if a function is differentiable, then it is continuous. Now, suppose a function is not continuous at a point, then can it be differentiable? If a function is not continuous, you have known it, that it is not continuous at a point. Can it be differentiable at that point? Anjali.
Yes, sir.
If a function is not continuous at a point, can it be differentiable at that point?
No, sir.
It cannot be, because this result tells you. It is like, suppose there is a the statement, if there is a flood, then crops will be destroyed. Okay. It definitely happens. If there is a flood, there will be water in the paddy field, then crops will be always destroyed. Suppose you have known this fact that there were no crops destroyed, then what can be your conclusion? Definitely, certainly there was no flood. Because if flood is there, crops are going to get destroyed. It is inevitable. Similar thing, if a function is differentiable, it must be continuous. So if it is not continuous, like you have known that at some place the crops were not destroyed, you can immediately conclude that obviously there was no flood. Similarly, if the function is not continuous, then you can conclude that the function is not differentiable. Here I am asking you that you tell me if is this function differentiable at this point I. One way I told you that you can go for this definition, and the other way is you check whether this function is continuous or not. This is far easier thing. If you can show that the function is not continuous, certainly it will not be differentiable. So first you check if this function is continuous at z equal to I. For continuity, you have this condition. If a function is continuous at a point, this condition must be satisfied. So you check if this condition is satisfied. Means means you have to check limit z tends to I, because our point here is I. Z tends to I, f of z equal to f of I or not. What will be f of I here?
I square plus
F of I. F of z equal to this. If z f of I equal to I. Okay. So you have to check limit z tends to I, f of z equal to what? Now you tell what will be this left hand side limit. Z tends to I, f of z. F of I we have got I. And what is limit z tends to I, f of z? Because finding limits you have learned already. That almost same thing for you can use apply your knowledge of finding limits for real functions. Z tends to I means this will come now. Z not equal to I. Z tends to I means Z not equal to I. So limit of this Z plus 1, Z tends to I will be what?
Zero, sir.
It will be 0 because yeah, this function is continuous. Because it will be not continuous if in the denominator you have something like infinity. So no, it is polynomial and polynomials are always continuous. When it is continuous, at the limiting point you can replace z by that point, z by I. So I square minus 1 plus 1 will get cancelled, will be equal to 0. So you will have limit z tends to I, f of z equal to 0, and f of I will be equal to I.
not continuous.
Are they equal? 0 and I. Are they equal? I is certainly not equal to 0. Is our conclusion. This function is continuous or not?
Not.
It is not continuous. So if it is not continuous, what is our conclusion? That it is not differentiable also. So this is the thing. So there is the same thing. F of I equal to I, but limit z tends to I. F z equal to I square plus 1 gives you 0, which is not equal to f of I. So therefore it is not continuous. So not continuous at I means not differentiable also. So there are two ways. First you can check by continuity, means it is the use of this result. If it is continuous, then you cannot conclude anything. If it is continuous, then also it may not be differentiable, so you have to go for previous technique by definition. But if it is not continuous, certainly you can conclude it is not differentiable. Now there are many other problems, and this should be all. You read them for understand. To understand something in class, we will. Okay. So far, if you have any question, do ask me. If not, then let me take your attendance. I'll share with you this notes and the ebook also, from which you read and try to understand the things in details. So we did.
Sir, I square is really an imaginary.
I square.
It's really an imaginary.
Tell me. Where? Square equal to what equal to minus 1. हाँ बोलो.
तो सर ये इमेजिनरी है या
रियल है या
इमेजिनरी?
आई स्क्वायर इक्वल टू तो माइनस 1 है, तो माइनस 1 इज रियल ओनली. I is imaginary, but square is real. तो उसका एक्सप्लेनेशन जैसे क्या बताया, आई का मतलब ज्योमेट्रिकली क्या होता है, ज्योमेट्रिकली इट इज ए पॉइंट ऑन द वाई एक्सिस, एक वन पॉजिटिवली डिस्टेंस पे जो पॉइंट है वो होता है आई, जीरो कोऑर्डिनेट पे जो पॉइंट है वो होता है आई आर्गन प्लेन पे। और आई स्क्वायर मतलब आई को आई से मल्टीप्लाई करने से वो रोटेट हो जाएगा बाई 90 डिग्री इन द एंटी क्लॉकवाइज डायरेक्शन। तो इसका एल्जेब्राइकली एक्सप्लेनेशन हमने देखा है कैसे होता है, तो वो उस पॉइंट पे आ जाएगा, वो रोटेट होने से उस पॉइंट पे आएगा -1 0, तो इसीलिए उसको हम -1 कहते हैं, आई स्क्वायर इक्वल टू -1, वो -1 एक रियल नंबर है। ठीक है, सो यू कैन से दैट आई इज ए complex number, but I square is real. But again, a real number, all real numbers are also complex number. If a real number is x, we can write it as x plus I 0, imaginary part 0. So real number is a subset of complex number. Inside complex numbers only. Okay, for answer of your question, real. Real means its imaginary part is 0. Attendance, Abhijit, Aditya, Adarsh, Anjali, Anku, Ankush, Arnav, Arnav. तो तुम लोगों को क्या लगता है, क्लास ऐसे ही ऑनलाइन चलना चाहिए या फिजिकली क्लास और एग्जाम शुरू होना चाहिए?
फिजिकली सर,
फिजिकली सर,
फिजिकली एग्जाम भी फिजिकली देना है?
यस सर।
Yes, sir.
ऑनलाइन
हाँ सर, फिजिकली अच्छा सर।
एग्जाम मजा नहीं आ रहा है?
ऑनलाइन नहीं है सर, नहीं सर,
नहीं है सर, फिजिकली बेस्ट था सर।
अरे बहुत लोग तो बोल रहे हैं कि ऑनलाइन एग्जाम होना चाहिए, कितना अच्छा है। वैसे मुझे भी कोई बुरा नहीं लग रहा है ऑनलाइन क्लास, बस वो एक्सप्लेनेशन में थोड़ा डिफिकल्ट। अरुणाव, तो ऑनलाइन का फेवर में कोई नहीं है क्या?
सर अपना अपना
स्टूडेंट्स जो देखता हूँ तो वो लोग तो ऑनलाइन
अलग 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 अलग
बेनिफिट है। एक्चुअली एग्जाम में किसी के लिए बेनिफिट है, किसी के लिए लॉस है, वो एग्जाम का पैटर्न पूरा चेंज हो जाता है, जैसे वो पॉजिटिवली स्क्यूड ग्राफ हो जाता है और एग्जाम का जो रियलिटी है वो नहीं रहता है।
और ये ऑनलाइन एक्सपीरियंस हो रहा है
बहरहाल हाँ, वो ये भी हो गया, वरना नहीं होता। किरण, ब्रसनंदा, वंशी, दीपज्योति, तो तुम्हारे स्टूडेंट ग्रुप में तो किसी का कोरोना इन्फेक्शन नहीं हुआ? किसी जान पहचान वालों का?
नहीं सर।
हुआ है?
जान पहचान में हुआ है सर।
एक तो तुम्हारा सीनियर का
जान पहचान में हुआ है सर।
किसका किसका हुआ है? एक तो मैंने सुना था तुम्हारा सीनियर, उसका नाम क्या था?
अभिमन्यु।
अभिमन्यु, हाँ, अभी तो क्यूर हो गया है। और किसी का हुआ है क्या?
नेबर्स वगैरह में होते रहते हैं।
Namal, Jatin, Dilip, Mana, Manish, Manthan, Yahayu, Nishant,